Cumulative distribution functions model the probability that some random variable will take on a value less than some specific value that we set. So we model them this way. This is what the equation looks like. We distinguish between probability mass functions and probability density functions and cumulative distribution functions by using this capital F. So with probability mass and probability density functions, we used a lowercase f. If you see a capital F, it means that we have transitioned to a cumulative distribution function instead. And what this says here is that the cumulative distribution function is equal to, this is the probability that our discrete random variable, capital X, takes on some value less than or equal to this value of X that we set. Now, we actually understand this better if we look at the graphs of the distributions for both discrete and continuous random variables. So let's start with a discrete random variable. So we're talking about discrete random variables here. We have already looked at the probability mass function for a discrete random variable. This is the one we've been using throughout these lessons. It's the probability mass function associated with rolling one six-sided die one time. And it shows us that a probability that we get a 1, 2, 3, 4, 5, or 6 when we roll the die is always equivalent. That's why we see that all of these bars have equal heights. The probability is always 1 over 6. The probability of rolling a 1 is 1 over 6. The probability of rolling a 2 is 1 over 6, etc. So this is the probability distribution showing the probability mass function for the discrete random variable. This graph on the right, on the other hand, is the cumulative distribution function that's associated with this same probability mass function. So if we were to transfer this information from the probability distribution over here to this cumulative distribution, this is how one graph translates to the other. In other words, this is the same probability here, the probability associated with rolling a six-sided die one time. We're just showing the cumulative distribution. And so what we're saying here when we look at the graph, or what this equation over here tells us, is that we can define this kind of cumulative probability. So instead of just saying what is the probability that we roll a 1 or roll a 4 or roll a 6, this is saying what is the probability that we roll a number less than or equal to 2, less than or equal to 4, or less than or equal to 6, for example. So that word cumulative is appropriate because the probability accumulates. And that idea of accumulation means that the cumulative distribution is always going to be increasing. And in fact, because we know that probability is always defined between 0 and 1, over here on the left edge of the graph of our cumulative distribution function, the probability that we see is 0. The value of the graph along the vertical axis here is at 0. And that probability is always going to increase and increase and increase as we move to the right until eventually it gets to 1. We see here we have 6 over 6, or 1. The probability tops out at 1. And so we say that the cumulative distribution has these properties, that the limit as x gets close to negative infinity is 0, and that the limit as x gets close to positive infinity is 1. Now this limit concept comes from calculus, and that's really beyond the scope of this course, but technically all this is really saying is that we're at a probability of 0 over here on the left, that's where this 0 comes from, and 1 over here on the right, that's where this 1 comes from. In other words, our cumulative distribution, the graph of our cumulative distribution, is always going to start at 1 and always increase and always end at positive 1, which makes sense because, again, we are accumulating probability as we move to the right. If we're rolling a six-sided die one time, the probability that we roll a value less than 1 is, of course, going to be 0 because the lowest value we can roll is a 1 itself. That's why we see this 0 value along the horizontal axis for these values less than 1. These empty circles here indicate that this value is not a part of the graph, whereas these solid filled-in circles indicate that this is a part of the graph. So what this tells us is that the probability that we roll a value less than or equal to 1, we come over to 1 along the horizontal axis, and then we go up and find the solid part of the graph, which is not this empty part here, but this solid part here. We come over to the vertical axis, and we see that this is 1 over 6. So the probability that we roll a value less than or equal to 1 is 1/6. The probability that we roll a value, let's say, less than or equal to 3, we come over to 3, we go up until we find a solid part of the graph. So we skip past this empty circle. We come up here, then we go over along to the vertical axis. This is at 3/6. So the probability that we roll a value less than or equal to 3 is 3/6. And that makes sense because less than or equal to 3 means we're rolling a 1, a 2, or a 3, which represents half of the total possibilities. And 3/6 is equal to 1/2. So we can see how those dice rolls are accumulating. And eventually we get to x equals 6 here, where we can say we come up to the solid part of the graph, and then we come over to the vertical axis, and we can see the probability 6/6 or 1 there. This is 1. So the probability that we roll a value less than or equal to 6 is, of course, 1. So that's what the cumulative distribution function is looking like for a discrete random variable. We are adding up all of those probabilities as we go. It would be like taking this graph of the probability mass function and adding each of these probabilities as we go. So the probability that we roll a 1 or less is 1/6. Then when we add another 1/6 to that, we can say that the probability of rolling a 2 or less is 2/6 or 1/3. The probability of rolling a 3 or less is 1/6 plus 1/6 plus 1/6 or 3/6 or 1/2. To give us yet another view on this, let's look at continuous random variables. So it's the same idea. We can use this cumulative distribution function for both discrete and continuous random variables. When we have a continuous random variable, the graph of our probability density function might look something like this. And if we transfer that over into a cumulative distribution function, we see how this probability accumulates starting down at 0 and continuing to accumulate probability all the way up until we get to 1, at which point it levels off and never rises above this value of 1. And we can imagine here that this sort of mean value in the probability density function is represented here in the cumulative distribution function. So we have those visuals. If we wanted to plug into the actual function here, let's say we wanted to model the probability for this discrete random variable representing the die roll. We wanted to model the probability of rolling something less than or equal to 4. Then our cumulative distribution function here would be capital F and then capital X, and then we would say of 4, lowercase x equal to 4, is the probability that the discrete random variable x takes on a value less than or equal to 4. If we wanted to say here for the continuous random variable, let's say that maybe this right here is x equals 2, and maybe roughly the same here is something like this, x equals 2. Then we could do the exact same thing for the continuous random variable and say that the cumulative distribution function, we have capital F, capital X of 2 is equal to the probability that the continuous random variable represented by capital X is less than or equal to 2. We would get that cumulative probability, the probability that this continuous random variable is taking on any value less than 2 or the exact value of 2. So anything up to and including 2. And we could find that probability on the graph by coming up from 2 here to the corresponding point on the graph, and then coming over here to the vertical axis. And this value along the vertical axis, let's say that's about 0.85 based on where we put in this 1 here. I'm just looking at the scale between 0 and 1 and estimating that that's about at 0.85. And so maybe if this is the shape of the cumulative distribution function, then the probability that the continuous random variable takes on a value less than or equal to 2 is approximately 0.85 or 85%. So again, instead of just modeling the probability of the discrete random variable taking on a specific value, taking on the specific value x equals 3, or for the continuous random variable in the probability density function, the probability that we take on a value between, let's say, 1 and 2, so take on some value between 1 and 2, that's what we did before with probability mass functions and probability density functions for discrete and continuous random variables respectively. Now, when we switch to cumulative distribution functions, we're looking at the probability that the random variable takes on some value up to some specified value, up to some specified value, instead of the probability of an exact value or the probability of some value in an interval. And then the only other thing we want to say about this is that we can use a cumulative distribution to find the probability that we do get a value in a particular interval. And we use this formula here. So if we have a cumulative distribution function, whether for a discrete random variable or a continuous random variable, we can use the values along the cumulative distribution function to find the probability that the random variable takes on a value in that interval. So for instance, going back to this discrete random variable, because we have concrete values here, it's easy to see. If we want to know the probability that when we roll the die, we get a value, let's say between 2 and 4, and notice this here notation less than and less than or equal to. So what we're saying is that we're looking for the probability that x is between 2 and 4, not including 2, but including 4. So if we have an interval here, 2, 3, 4, we're not including 2, but we are including 4. So the only values that would actually fall within this interval are the values 3 and 4. So we set that up, and then we look at our cumulative distribution indicated by this capital F, and we find the value of that cumulative distribution function at b. So b is 4, we come here to 4, and we see that up at 4 here, we're at 4 over 6, which is 2/3. So we get 2/3, and then we subtract the value of the cumulative distribution function evaluated at a. Well, a is 2, so we come up here to 2. We come up to the solid circle, come over to the vertical axis, and we see there 2 over 6, or 1/3. So we subtract 1/3, and the result then, 2 over 3 minus 1 over 3 is 1/3. So this tells us that the probability that we get a value between 2 and 4, not including 2, but including 4, is 1/3. And of course, that makes sense because we said here that this expression showing this interval implies getting either a 3 or a 4. Those are the only two values that fall within this interval. And of course, out of 6 possibilities, when we roll the die, getting anywhere from a 1 to a 6, there are 6 possibilities. There are 2 possibilities of those 6 that meet this criteria that fall within this interval. So out of the 6 total possibilities, there are 2 that fall within the interval. And of course, that simplifies to 1/3. 1/3 of our possibilities meet this interval, meet this criteria. And so the probability that we fall within this interval is 1/3. So we can also use our cumulative distribution, whether it's for a discrete or continuous random variable, to calculate the probability that the random variable will take on a value in this particular interval.